All right. And welcome to Adjunct of Computing. This is for episode 184 of Advent of Computing. That is called, What is a Programming Language? And
it's a good question, Joe.
What is a programming language?
Well, not just any programming language,
a programming language. That's what I'm asking.
Oh my God, that's such a dumb name. Like, I get that it's early. You can name it anything you want. That's so ambiguous. Like, just
do you think there's any aspect here of, and I'm sure it's completely just like, whoopsie, I didn't think too hard about this and didn't think it was a big deal. Or do you think there's an aspect a little bit to this of, I'm going to write the papers about this and whatnot and just like stake my claim on making this a programming language?
The vibe that I guess, and again, guess, is that it was a joke, since it's based off the paper A programming language and then becomes the name of the language described in the paper A programming language. That seems like I forget the guy in the crew that actually suggested that name, but it really seems like haha. That would be so funny, wouldn't it? We should do that.
I mean, that seems like the natural follow-on, because that's a theme that I've said before. That is a theme with nerds, engineers, those types.
We like jokes.
They love a good dumb joke. They love to name things. I mean, the entirety of GNU.
You mean new?
Sorry. Yeah, new.
Can I have a fight? That'd be a good episode. No, that would be bad radio.
And that's because I legitimately don't know. It's always, I've never brought it up before, but it's always fascinating listening to your episodes and realizing that a bunch of these names and whatnot are things that I've only read. And like that comes up all the time, especially in like research things. But like, is it Everson? I always thought it was Iverson, and I'm not sure I've ever actually heard it.
So,
and yet, like, my brain, it's one of those things where your brain swears to God you've heard it, and I'm just racking my brains, and I'm like,
I don't usually
I've never heard that.
Look up audio interviews with people. I usually use transcripts because I can full text search, so that makes it easier to reference than when I go back. So I don't know. It could be Everson or Iverson. But the phenomenon I've noticed is no matter how I pronounce names, it's like a 50-50 chance if I'll get an email saying I was wrong.
Well, that's why I've never brought it up too, because I know this is such a thing. Yeah. And I know I'm probably going to be wrong about 50% of the time, and you're going to be wrong about 50% of the time. And honestly, it doesn't matter as much as like the story.
When I did the Ada episodes, I did the first part of that, and I pronounced it Ada, and got a couple of emails saying, well, it's actually pronounced Ada. And so I switched to that pronunciation because they had some reasonable arguments. And then when I put out the second episode and pronounced it Ada, and even mentioned, I'm trying to use the correct pronunciation, I got a couple emails saying, actually, it's pronounced Ada. You were right the first time.
Nice.
So,
whatever. That's why I say, I mean, it's better to get things right if one can, but the important part is the story and the context.
So what's the story this time, Joe? What have you brought to me?
Well, can I get us like right off to a tangent, because you said Ada, and I have to mention the Babbage thing.
Oh,
just because I texted that to you. And for people listening, this has nothing to do with anything, but I like
Babbage is foundational. This has to do with everything.
He is foundational, but like,
if you believe in that lineage.
I started like, I just listened to lately. I've been listening to like historical audiobooks at night, and so I needed a fresh one, and so I got Babbage's memoirs. People, go read Babbage's memoirs. I'm listening to it on LibriVox. I didn't either. I was just like, every now and then I go on LibriVox and my Audible credits are out. So I was just like, I'll go back to LibriVox because there's some decent stuff there, and it's free, and it's great that people try and do this, but it doesn't matter that like the narrations are, average person quality on this thing, because it is just, okay. So I'll get past it, but just the first chapter, he talks about his youth where he was struggling with religion and decided just out of curiosity to go make a magic circle with his own blood and summon the devil.
I mean,
and then like it didn't work, and he was like, sure, I don't know about all this.
Maybe I'll get really into math in a weird way. Yeah. Maybe that's the remedy. That's hilarious. And I should listen to that audiobook or just read it. Because
it was just that it's so unexpected, and so I just need to get that out into the world, because oh my God.
I knew Babbage was a biblical scholar.
Was he?
Think.
Because that's another thing. I don't know that much about him.
I could be talking out of turn. I seem to remember that he published a treatise on some biblical texts in addition.
I mean, the impression I get is that he's just one of those Victorian polymath types. So that
don't fact check me. Likely wrong. But I know
this
there's
show
someone
isn't here for. This show is only here for factoids.
Yes. The oids, not the facts.
I've learned recently, besides this, Victorians are funny as hell.
Yeah. Well,
they are super funny.
They have names like Poop Crump.
That's true, but I didn't expect that like they would actually be self-aware as to how hilarious these things are. Anyway, not that all things about the Victorians are good, but I'm glad to have been learning that. Let's get back to APL. That is the subject. You tell us about APL. This is the part of the show where I'm supposed to be asking you, you're supposed to be telling me what went on, what on earth is a programming language.
So
I understand that it's very straightforward.
APL, very funny joke. It's a functional programming language, and it's not a list-oriented language in the same way that Lisp is, but it's built to work with lists and vectors and matrices and higher order data structures. The knockdown feature of it is that it uses a custom character set. So this is how I opened the episode, right? Is if you ever see APL in the wild and you're not ready for it, it doesn't look like a programming language. Even though it is a programming language, don't look right. It looks like math. It looks like secret special magic math.
Well, I mean, and it is, right? That's one of the things.
It is
that's
math.
like the first half of the episode really is
that's
talking
the
about
surprise.
How that's the point.
Yeah, is APL is developed to be computer math, kind of. That's really hand-wavy as an explanation, but it's kind of computer math. Mm-hmm. And it eventually goes from being a notation to mathematize computers, for lack of a better term, to becoming a notation used for describing computers, and then becoming a programming language that can run on computers. And all along the way, it's getting more and more... Fiddly's not the right word. The syntax gets more and more separated from traditional math syntax, to the point where by the time it's an actual functional programming language, it has a full custom character set. And each function is represented by a special glyph, basically a hieroglyphic.
An actual functional programming language, you say? Because I've gotten my notes, because I know it was stuck in there at the very front of the episode just for me, because I was saying, isn't APL, isn't it like, it's a functional programming language effectively, I'm fairly certain.
Well, a little bit. I have some questions for you about that, Joe.
And it's because I have a whole back half, and I want to preface before we even get there, and I hope it'll be a while, hopefully, before we get there, because we have a whole bunch to talk about APL before we approach that area. But I have functional notes, but I do want to preface always because functional people are usually pretty cool, but it's also usually people who like people either get into functional or like don't.
And as we've established on the show, I'm an oops guy. I don't think in functional, and you're a functional guy. You don't think in oops.
I like everything. I think all programming languages are interesting.
That's exactly what a functional guy would say to me.
Yeah. But my point is,
I'm not dogmatic at all.
I am very I dabble in functional stuff, and I just think it's rad concepts. So for any people who actually know what they're talking about out there, as always with everything that we do, be prepared to be like, oh my God, this guy doesn't know what he's talking about. Even though I'm the one who is, as I inform Sean incorrectly, that's going to be the meta there. All right, so that is the big long and short. Is APL is old. It's strange paradigm.
1954 old.
Yeah, and I just have some. As always, that I've decided to just put them at the front because there isn't a lot of commentary to say about them, but just things that you say in the show that I think are a hoot and I want to mess about. The first one is just the functional thing, just because I had mentioned that and I was like, haha. I enjoy trad math is great.
Yeah, no, I got sick of writing traditional.
I know. I just one of the I'm going to use that term from now on, and or alternatively, maybe cis math
No, because transitive's a thing in mathematics. I think that
is true.
Yeah, that can be too confusing.
No, cis math is math that involves no transcendental numbers. I don't know if that even works as a pun.
That's bad. No, I like I said on the show, I like trad math because that does imply so much that doesn't exist.
Yeah.
Like, is there left wing and right wing mathematics?
Traditional
Maybe.
versus weirdo math is it's a great nonsense delineation. And on that note, I mean, we could just chat for a minute about linear algebra being neat. And I wish I was better at it because it's just a subject that you dive into there. And a lot of just like APL functionally deals with or is very good at linear algebra because it's all matrix and vector. And
yes,
I've always been confused about this. And I don't know if you know, because we famously talk about not being math guys.
I mean, I'm only
is a tensor just a higher? A tensor is just any higher dimensional
vector. A tensor
vector?
is specifically a fourth dimensional vector. Yeah,
it's specifically. I've always wondered about that.
I joke about not being a math guy. It's that I'm rusty. I have a degree in
you have a
astrophysics.
physics degree.
Yeah, I was like 2 classes away from having a bachelor's in mathematics. So I'm like my capstone project
that
was
kind of stuff is
literal tensor mathematics. And then converting that into a computer simulation. So I know a little bit about
at one point.
Linear, a little bit. I can tell you a dumb story about linear algebra, though.
Please, we're all here for dumb stories.
I recommend if a listener out there is in college and has the opportunity, take a course in linear algebra. It's very, very interesting. When I took a linear course in my physics undergrad, I was sitting next to one of my colleagues that I took like almost every class with, and he wasn't a programmer. I was already at the time. That's how I paid my way through college.
Nice.
As one does, you know. But
that's how it's done.
We're sitting there and like, I'm enjoying the class because the math is really simple to me. Because, you know, instantly it's pretty easy to realize that, oh, this is just arrays and lists. I know how a for loop works. So, like, even without using a language with array broadcasting, I can just, like, do my homework. I ended up doing a lot of my homework in Python because it does have array broadcasting if you do it right. I'm pretty sure.
Python's funny like that because it has so many...
Well, it has lists and arrays, things. But whatever. Yeah. But the guy I was taking the class with didn't know how to program, and so he's struggling through all of it. And I'm like, no, it's easy. It's just for loops. Like, you can just do it like this. And he's like, I just don't get it. And like a few weeks before the class ends, we're at another friend's house drinking, and he corners me drunk in the kitchen, and he's like, Sean, someone explain for loops to me. And I just intrinsically understood how it works now. I think I understand linear algebra. And I'm like, good, you got there. I was telling you it's just like programming. He's like, well, I think I have an intrinsic aptitude for programming. I think that's what I've discovered. It's like, no, that's not where this conversation should be going. This should be going towards, I'm going to pass my linear final because I learned about programming.
Oh, no, he didn't get like obsessed. He didn't go down the obsessive programming track, did he?
No,
that's the danger there.
He wasn't good at programming. He really got loops all of a sudden, and that was it. That was enough for him. It's like, I mean, I'm sure I get all of it now.
This is what I think about APL. This is why I would like to learn to bring it back a little bit, at least to topical. I'm going to dive off on my own stories in a second here anyway, too. But that's exactly why I wanted to learn APL for this. And I am so sad that I didn't, and we'll get back to that. But just I remember that feeling. I can understand that feeling that he had because like learning a new paradigm of anything, especially in programming.
Well, it's mind blowing.
It's like when I finally grokked a bunch of functional concepts. And like your brain just turns upside down, and now you understand a whole different way of looking. Well,
especially
things.
if you can apply.
And I want to do that with APL.
Instantly.
That feels like the way, like one of the ones that will just make it. You know, I'll be like, oh, that's interesting.
I was trying to learn APL, and I haven't quite got there.
I mean, you had like 2 weeks. It's not a lot of time.
I had 3 weeks because remember I extended
big difference.
The time. I know more about APL than I know APL. Let's just put it that way. But that's usually how how it goes with me.
I mean, that's research in general, especially when you're picking out a new thing every couple weeks. But yeah, my story on linear algebra is, I don't have much. So I don't know if I've talked about my background. I'm a community college dropout personally, and so I'm ADHD. This is like I can't stay in a class. I'm that guy. I know too much about weird things,
dude. That's why I didn't go for a graduate degree. I didn't want to sit in the class ever again.
That is fair.
Oh my god.
But so mine is we did, some basic linear algebra stuff in high school, and then I never saw it again. And I mean, even like I got up to my Calc 2 and whatnot. But then when I I worked at Toyota for a while, and it was involved with CAD stuff and doing a lot of drawing generation. And so
that's
we were doing
linear algebra.
Right
there.
And so not wanting to look silly, so we're working on like drawing generation tools, and my boss, thankfully very, very chill guy, and we're this very small group, but he's just like, one day he's like, okay, I want to see if you can work on this project. I'm going to hand it over to you. You know linear algebra, right? And I was like, yeah.
Sure.
Yeah. But it was great because I think that's one of the reasons that I like it, that I can appreciate it is that on the job training and like figuring out, because I had to intuitively understand like what dot product and whatnot mean.
Oh no.
but that's great because you have to like I was looking at the stuff and I'm like, why a dot product? Why is this doing that? And then like I had to grok it, and I understand not like how to do my homework. I understand like, oh, that's why you do this, because it's effectively, it calculates the angle between these two things.
That's like the difference,
the projection of the thing on the other thing.
Between learning, right, and that moment of realization, like you were talking about.
Exactly.
Is when you can understand something and apply it instantly. You get that instant feedback. That's addictive. That's a lot more addictive than like reading a dot product is described as ...
Yep. Super interesting. I wish I, because that's how I learn personally, and I wish I could find a way to like make that happen automatically. Then I would be much better at things. But
just
anyhow,
the dopamine button.
Yes, APL is a linear algebra machine. And move past all the linear algebra stuff because I dwelt on that for even longer than I would like to.
So the outer product is defined as...
Yes, so let's go through all the definitions. We are now starting a multi-episode primer.
We're just talking, this is now the linear algebra cast.
Yeah.
We're just describing math.
It's extremely... The reason to dwell on it, this will get us out of it, and it's why... I could
the only escape is to
about
dwell.
That makes sense in the context of APL, because if I learned anything from 3 Blue 1 Brown, like you can describe everything in linear algebra, or vector calculus.
You can describe everything computable with linear algebra,
right? So it's like perfect. It makes sense to me. Right. And again, like you said, because it's all for loops, or it's all it's arrays of data. Yeah. Actually, I'm remembering now, in the episode you said something about like, you said computers are
just machines that simulate mathematics, and
you can describe them with linear algebra machines.
Yeah.
And at first I was like, I don't know. But then as I was thinking about it and you were talking about it, and I think you say something in the episode, it's just like all of a sudden I was like, oh yeah, because memory is an intrinsic part of the computer, and it's a
you can describe it as a vector
that you can then,
and you can manipulate.
You could describe it as any n-dimensional vector if you want to think of it that way too. And all of a sudden, I was like,
a state transition is just an operation that operates on a vector, and the vector is the state of the computer.
So you do understand functional programming.
That's not.
So that's the thing. We'll get there, but that's the thing you need. That's the realization that makes functional like doable. Anyway. Let's just take like this is a great place to take a turn. And one thing that I did in my limited amount of time that I had to like do research, that I as much as I could about APL.
You went to tryapl.org and you did the tutorial.
I'm sure I clicked like that. I know exactly what you're talking about. I'm not sure if I actually went to it. But the one thing that I didn't realize, that the character set is alive and well.
Yeah, no, it's a Unicode page, I think.
And I'm not surprised that it's a Unicode page per se, but that like I go into the tutorial and I'm figuring this day and age, It's like either they've got mappings or they've got human readable,
No, it's
more
a straight
English
up-
language versions
it's a
of all
straight
the
up care set
operators
still.
that you can write in these days. No, the first thing they instruct you is like in your IDE, you will set up your key mapping. Mm-hmm. And that's amazing.
Well, you
like,
have to.
I get it. I understand. It's just that I would have assumed that's such a pain in the ass. That is such a barrier to entry, you know? I am not faulting the language. I just think that's amazing that at this point it exists, it's used.
It's APL is so obscure. Or at least
of course.
To the modern programmer, APL is pretty obscure. Because it's a custom character.
It's very
we have
niche
support for it. Yeah, that too.
That's, I will say as an aside, the Toyota thing reminded me when I started working at Toyota all those many years ago, the thing going around was R. A bunch of people were talking about R, which is a child of APL. And that's the wild thing to me is I didn't realize at that time that R was a thing, but I just very much remember at that time all of the engineering nerds were talking about using R for stat stuff and it was hot at the moment for some reason.
Yeah, I remember all the engineering students talking about R at my college, and I was always like, oh, that's very interesting. And then I'd walk away from them because we had a math lab license, or no, we had a Mathematica license. So I'm like, why would you use R? Mathematica is very cool, in fact. But that's also, I think, somehow related to a revival of APL.
Yes. Yeah, it's a direct descendant of a very directly inspired by APL language or something.
I want to say S.
It's a statistics language called S. That is it's basically based on APL, and then R is a descendant of it. So it's used, and it's active, which is wild because again, what's the 50? You remember off the top of your head, and I'm scanning the document. The first
Why would I remember
year,
anything?
Yeah, I know.
Oh, APL's notation is used in 1954 in a college class.
The notation is 54. That's what he does his class.
But it's not quite APL notation.
Right. And
it's still weird.
This is the part of the story is that it takes so long for it to be implemented.
Well, Lisp did a similar thing, and it's why I'll go to blows with people who say, oh, Lisp is from 1958. It's a form of Lisp was theorized in 1958, and then it was implemented as something that looks like Lisp in 1960. APL is similar, where it kind of spins around for 7 years before it's
interesting with APL because it spins around as totally not a language at all.
Yeah.
Or not computer implemented at all. At least Lisp. Because the thing I think is interesting about Lisp, and it gives me an in because I wanted to mention Lisp stuff, is that Lisp is interesting in that, like you say, it's in a form in 58, even in 60. But the thing that, oh my gosh, and his name is escaping me, but good old Graybeard, the Lisp guy. No, I look at, he just looks like the classic Graybeard. I'm sorry.
I know who you mean.
Was offensive
the name also escapes me, but that's also 50.
John something. That kills me. He's a very famous person.
McCarthy. John McCarthy.
McCarthy.
Yeah.
Is that Lisp is almost not even really a thing, if that makes sense. Lineage-wise, there was kind of this thing he made, and it was a very influx thing.
Well, and the
and there was
paper,
there was Lisp 1 and Lisp 1.5, but really, when you think about Lisp today, you're thinking about
you're thinking about S expressions, and the 58 paper
and
included S and M expressions,
because
which are never implemented because you don't need two syntaxes. That's what's so cool about Lisp is it's one syntax for everything, including the meta language.
And that's one of the terrible things about Lisp is it has zero syntax.
No, it does have syntax, kind of. It's just very, very smart syntax.
But I'll move on from Lisp because like I was about to say, it's not a Lisp episode, and I'm sure Lisp will come up many times in the future. But
I'm never talking about Lisp again. Actually, I've taken a vow.
Good,
yeah.
Honestly, that's probably for the best. Lisp is not a functional language.
Why?
Scheme is a functional language.
Scheme is a derivative of Lisp. What are you talking about?
It is, but Scheme. Well, see, that's why I'm saying about the thing about Lisp is that Lisp is more of a way. Lisp is more syntactic and ideological than it is semantic. because
What?
original Lisp
What does that mean?
is basically an imperative language. It has its Lisp processing stuff, but it really doesn't have, and this I won't say like with absolute, but it doesn't have a lot of dedicated support around first class functions. I'm not sure if you can def a first class function, but that's the thing about Scheme, is that Scheme really is a thing where they looked at it and they said, this looks a lot like lambda calculus, which never was McCarthy's original. He's talked about that. He's like, I didn't even really know about lambda calculus at the time. It doesn't really have anything to do with it. It just has a lot of parentheses. And the scheme guys were like, let's apply lambda calculus to this syntax, and we'll introduce a bunch of operators and stuff. That's the thing about Lisp is that
why are you doing this to me, Joe?
I know. I'm sorry. And we'll move on. It's not a Lisp episode.
I thought defun was a Lisp primitive, and that defines a function. Okay.
That's the thing. That's why I'm saying I don't know the extent of what primitives existed at the time, because Lisp has a lot of weird stuff. Because it also has
and admittedly, I learned on Common Lisp, so I don't have the syntax for early Lisp. And I think
Common Lisp includes a lot of scheme stuff. Like most of the time when people think about Lisp, they're thinking about scheme type languages.
I gotta do an episode on that now. I said I was never talking about Lisp again, and you ruined it. My vow is broken.
Is this our first language episode that we've done?
I don't think so.
Like we've gotten this deep, but have we have done a language before? Because there's a handful of episodes.
Let's look at this. We did programming block by block. We did GPSS, but that's but that was more not a programming language,
right? And that kind of ends up being almost an operating systems episode.
Well, I mean, what's the difference between a language and an operating system, really?
That is true. But
on topic,
which we really are, because what I was trying to say is there's a ton here, and for the audience, I assume this is good stuff, and I hope you're having a good time, because this is the crazy info dump we do, and that's the point. But that it's occurring to me because this is all coming up because I don't think we've talked languages before, and that's a deep hole. You and me have talked personally about language stuff, but I'll try and rein it in for more stuff later. For APL, let's, at this point, because I feel like we're probably about halfway into our episode at this point, let's talk about some of the more history APL stuff, because one could talk about the syntax and whatnot, and it's not like, I feel like as a listener or anybody who's interested, I feel like you'd have to go learn something like this, Yeah, like you can talk about I
agree. One thing that more and more I've been forming an opinion about is it's really hard to talk about syntax over audio. So I've been trying to do less of that on the podcast and more talk about how the syntax relates to other syntaxes, or how it relates to other concepts, instead of the upside down Christmas tree is crucially important, but not as important as the row. And here's how you operate with the row, because that's information, but it's not
historical family tree.
Nice information.
Is much more. It's the historical family tree is probably more interesting, and I think just languages are so deep. A lot of the understanding what a language is is you have to sit down with it and get a feel for the emergent behaviors that happen as you try and do something with it. You know what I mean?
the secret operators.
Yeah. But that generally, so I mean, if you haven't, go back and listen to the episode, I guess is what I'm going to say, because I was going to say a bunch of description of the language, but to make a long story short, it is, as we said at the beginning, it operates on matrices, and fundamentally, actually we can poke a little bit.
It operates on any data structure, actually, as long as it's something like a list.
Right, but n-dimensional things.
For many values of list.
Yes, for many dimensions of list. And the other thing is, because we keep talking functional, and people might be wondering why is that even coming up. It's because it's basically built out of composing operations to a certain extent, right? So that's what I was going to ask, is as far as you actually learning it, how accurate is that Because that's my vague understanding.
Completely
still
accurate.
not having any.
So
okay.
So qualifier, I've only gone through the tryapl.org tutorials because that is the most accessible way to try apl.org. God, that's bad. That's a bad joke.
No, I mean, I feel like anybody hawking APL at this point, they need the advertisement.
Yeah, so I've gone through the tutorial there. It's pretty good. And I've done just a little poking around. Not like I don't think I've even gotten as complicated as doing a FizzBuzz with it. But it is very much, it's like writing down a mathematical equation that executes. Mm-hmm. Sorry, the dog is here and shaking. So it is very much composing operations.
And is it, because you can literally, like, composition is part of, is it like juxtaposition of two things composes those two operations with each other?
No. So
like, how does your f of g happen?
f of g uses a thing called a train.
Okay.
Which I don't understand. There's specific precedence orders for how you resolve a train. So you can do like plus minus, well, you can do like 1 plus minus 1, and that does like the f of g of arg. And you can do like trains up to 3, and then once you get up to 3, it just recursively applies the rule. So you can do like argument and then like 20 characters and then your next argument. And there's a way that it resolves is application.
Making me, it's like raising my hackles in that. And
yeah.
I know APL is weird, but anytime you get like you can apply n number of operations and then it becomes a special case.
Yeah.
The
special case is 1, 2,
language.
3, and then it recursively applies. I think that's the right word, but it applies the same rule set to decompose it down to 3.
Okay.
Yeah.
That's interesting.
Yeah,
I love the thing that immediately is brought to mind. It's not the most relevant thing. It's just that it comes to mind is special cases and n number of things. Is I love tuples in C#. I do C# for a living. It is all they are fixed size. Tuples are not of arbitrary size, and they're all a distinct type because tuples were not an original part of C#.
That's weird.
So they're just there's a distinct type for a 1 tuple, a 2 tuple, a 3 tuple, and they go up to like 9 tuple or something.
Wait, so it's
and
just
that's as far as the standard library goes. And if you want to pass a 9 tuple, you can't do it.
Exposes a class, like a set of 9 different classes. That's janky. I kind of like it.
It's really janky. It's fantastic.
So the other weird thing in APL, well, another weird thing is, so normally the characters like plus, minus, even comparators are functions. But what APL calls operators are functions that take as arguments other functions and, do stuff with those. So you can build really complicated expressions with like just a handful of characters.
And that lets me get through one of my quick FP notes that doesn't deserve a lot of time, so it's good time for it, is that is known in functional programming as a combinator, generally.
Okay.
So if you ever hear combinator, and as far as I understand, combinator is kind of one of those made-up computer terms where like it could mean like a function, or it could mean, but what I've understood is that generally people agree on that a combinator is a function that takes a function and produces a function. So like if it takes any scalars or non-functionals, then it's not a combinator. But so as soon as you said operators, I was like, yep, FP stuff, that's a combinator. What they're calling operators are combinators.
Well, you see, like I said, I'm not in this world. I don't know all the little social details correctly.
Which is what they are, because it's all, I mean, like all words, it's all made up, it's all jargon. Historical stuff.
Yes.
That I had, you know what, let me dive into the paper that I was asking you about just earlier, because I did the same thing that I did for the... Find it? No, but it's not a big deal because I don't think it would be worth digging. It wouldn't give me any more to dig into.
So what is it? What do you got for me?
It's not as deep of a cool thing as looking up the casting out nines is parody thing. But what I'm about 99% certain of now, that I was about 80% certain of when I was listening to the episode, is in the episode, audience, it is described that at some point Iverson goes to work at IBM, and he is involved with. Let's see if you can remember a name off the top of your head, because this is one that I don't have. Mythical Man Month guy.
Oh, Fred Brooks. Doctors. They're all doctors. Every single one of the people involved with this has a PhD.
Having management at IBM and you're not a PhD, I mean, that seems
Get out of here. Impossible.
Yeah, completely believable.
How are you going to be in the 100%er club if you don't have a PhD?
And your blue suit, as mentioned.
Gotta have a blue suit.
Gotta have your blue suit. Anyhow, so he goes to IBM, and the 360 is described in like a subset of APL. They do a formal definition of the ISA of the 360. And my eyes lit up because I might have to run, and I would even put a cut in this episode because I meant to grab a book or two before this episode that I didn't have time to look at. Anyway, there is this thing called it's a very broad brush thing called RTL, Register Transfer Language. And
like a microcode language?
Ish. So this is the thing, is it's not well defined. It's sort of not well defined and is. I've seen it pop up a bunch of places, and this is where the fun ones always are. And I know I've seen it in, I think I've seen it in one of my books. That was what I was going to grab. But RTL is really all it is describing inputs in some expression are on this side, and they go into this register, right? So it's like, if you're going to describe the add operation on your 360, the add itself would be, register A plus register B into register C, right? Whatever that is. It is well defined, and this I actually didn't know much about until I was trying to look this stuff up and find the connection. It's semi-formalized in that it's used, a thing called RTL, which is the same thing in different guise, is used as an intermediate language in some compilers and some historical compilers. I'm not sure.
Sorry, I gotta go kick the boy to the curb.
You said it was going to happen.
He decided it's time.
No, that's perfect. We'll cut here, and I will get my book.
This is the lad, Publius. All right, so what were you talking about before the boy?
We'll put an edit in here.
Yeah.
And I'll flip through. So I might be totally wrong, but it's either in...
Oh, is that Nuth?
That's Nuth.
Which volume?
1. This one I picked up off of thrift books. I didn't even know what it was when I got it. I was just like, that sounds neat.
That sounds useful.
So, yeah, this was crazy because then I went back to it and I was like, oh, holy crap. Apparently this one is also a classic, but Computer Architecture, A Quantitative Approach.
I don't have that one.
And so I'm just going to scan this really quick because I swear it's the way you also see algorithms books sometimes use RTL in that way. Anyhow, I'll check these books again sometime later. I'll see if I can turn it up. But I've seen it as a common thing, and it seems like it's used as a intermediate language and stuff. The whole point is
so we're here.
I think it comes from this IBM thing that you're talking about.
We're just reading Nuth live. Is that what we're doing now?
Chapter 1.
In the beginning, there was
algorithms. Anyway, so I think that's interesting. I'd like to try and connect that more, but that's why I say I don't think finding that paper in particular, it'd probably be interesting to read, but there's a pretty clear connection here in that it is clearly documented that they used this APL derivative or this version of APL.
Well, that was used after the ISA was defined already.
Right, but it was used.
It was used
to document it effectively.
Yeah, at least as an exercise.
And the paper that I was showing you that I don't have access to calls it it's at the right time. It is by an IBM person, and it is talking about computer design using a register transfer language.
Interesting.
It's that left-facing arrow it's not uncommon, but for it to be the APL assignment thing, for it to be the IBM used in the 360s documentation, formal documentation of the ISA, and this paper from the same time calls that process using a register transfer language. I
is
think that's
really
what the lineage
interesting.
is, and that's so cool.
So I'd be curious to try and track down the actual documents that were used to define the 360 ISA, because those won't be in APL, right?
Right.
But I'm curious now what they are in, because there must have been, there was a formal definition process.
Mm-hmm.
So I'm curious if it is prose or if it is RTL, like you're saying, or if it is like some like nicer setup.
Yeah.
And it might have the backwards arrows.
But that was RTL is just a thing that randomly came up in my past, had it in the back of my head, and it just struck me as, oh, is that thing?
I should
and
keep my
swore
eyes
I had
open.
seen it in IBM related stuff, and I think it is. So that's kind of neat. This is good. Oh, also, I was just going to talk generally about that left-facing arrow being it's an interesting, unique thing to APL, and I wonder if, APL is so old, it's got to be the progenitor of this in general, or at least the inspiring thing of a lot of things that do that. But
I'd push back on that a little bit, because it's such a such a natural thing to do. Be like, this value, that I'm pointing at it.
I know, though, I had never, I think TI Basic, the graphing calculator basic, I'm pretty sure it uses left arrow for assignments. And so it's that I know I've seen that in a bunch of, especially when it tends to be more mathematical, like programming that is very in the math wheelhouse, which is an APL.
Joe, look, someone is going to say, oh, well, that's used in this specific type of mathematics, and we're going to look like fools.
Probably. Math and logic is rife with the usage of funny symbols
used in logic. But like I was saying, I think you could probably build up a lineage, or probably a few lineages of languages that use left arrows, but I don't think I'd treat it as diagnostic of a language being related to APL if it just used the arrow. Right.
Sure. And I didn't mean to imply, that's why I was trying to kind of hedge there with, at least inspired by, or that.
There's a touch of the stuff.
Yeah. Kind of like in the same way that a lot of stuff, it kind of comes from Algol without being from Algol.
Oh, yeah. Okay. I gotcha. Yeah.
Yeah. Where just like someone came up with that, and then all of a sudden it's like, oh, well, this seems like, this is clearly we're getting into programming languages for the first time episode, because I've got so much stuff in that. Like I was looking at the progenitor of B's parent,
BCPL,
and CPL stuff. But that there's something about languages from back then that just speaking of the inspiration of things, and this is just a random thing that I was thinking about the other day. It's so interesting how it seems to have started out with languages, and that APL is such a knot of this lineage, that it starts with linguistics, and that it's almost like trying to do natural language with a computer.
Yeah,
and,
that's what
you've got all your Chomsky stuff. And so there are so many early programming languages, like BCPL, the parent of C, has like so much extra verbose syntax in it that like just makes it read
well, it's different schools of thought, right?
In where thing is, it's different schools of thought, but it's just so funny to see, like, we're used to programming languages being more terse these days, where it's like, let's take the keyword, like, screw Algol and Pascal, let's not have beginning and ends. Just that's, I think, why BCPL and coming down to C makes that stick out to me, because they were just, the BCPL guy was just like, why beginning and end? I'm going to just use a couple glyphs for opening and closing these things.
Well, I think it just gets simplified,
and you get to the pure thing of what a programming language really is and feels like today, except for APL.
Well, I'd be careful about using the word purity with programming languages. I think it's more that you're pointing out how different languages have different design goals, right?
Sure.
And that's going to dictate what it looks like, what it can do, and who enjoys it. Like COBOL, we would die if we were exposed to raw COBOL, but some people like it. And it was designed for specific reasons that at the time were good and important.
And that comes right off of COBOL as one that was designed to be very natural language.
Yeah.
It's really bizarre. I didn't realize how natural language. I've always pictured COBOL being more like Fortran for some reason. And just
it's
like a
all
couple years
caps.
ago, I was like, I'm going to finally like look at COBOL, and it's like, it reads, it's sentences. There are so few symbols. In
Instantly have a freak
it's like
out.
the opposite of APL. It is the most verbose language.
So we got to do the APL to COBOL scale now for all syntaxes.
No, that's perfect. When we do language episodes again, I'm going to write that down as an idea because I legitimately think that is a good scale. Algol 60 is like right in the middle, and then COBOL is over here. Yeah.
I think Algol is probably a little COBOL-y.
Yeah.
It has
You think
words.
it's more COBOL? You think it's more COBOL than...
well, it has full English words in it, right?
It does. But, like, I mean, COBOL has... I'll say... Because COBOL has, like, so much, like, unnecessary words, right? Like just stuff that's put in there, almost like that things that, like, Intercal and stuff is making fun of. Yeah. Because there are, like, verbose bits of syntax in there that actually serve no function, but they make it look more like
the function is it's pretty.
Yeah, I mean, truly, that makes it interface to humans.
So
but that doesn't actually serve a syntactic purpose.
So APL's doing something.
APL's doing something, and it's definitely on the end of a scale there. Oh my gosh. One thing I'll say is that it's a really cool link that, I mean, it kind of, the link of people in this story.
Oh yeah,
is kind of wild in that, like, and that these are also all players that, like, I want to know more about each one individually, and then they just all come together in this episode. And now I'm like, well, now I have to research each of these people more individually because I know their contributions.
I've succeeded.
Yeah, the lineage from Howard Aiken into Kenneth Everson into Fred Brooks, and that's just, I mean, I guess it's not, when you sit down and think it through, Aiken to Brooks is not too crazy in that they're both IBM related people. Or I guess because Aiken isn't IBM, right? He's Harvard,
but he worked really close with IBM.
He worked
during
closely
the
with
Mark
IBM,
I.
but he was never an IBM person. Right. But so there's that linkage there. But still, that is so good. It's that funny. Kenneth Iverson just kind of exists as this missing link between Harvard and the Mark I world.
Iverson and Brooks
IBM
were both students under Aiken at Harvard.
Did you say that in the story? That might have been something that just flew right by me.
Did. I might have implied it just because Brooks was a teaching assistant under Everson, and they both got their doctorates advised by Aiken.
It's possible. I know there's a little bit of a. I know I missed a little bit in that transitional section when I was listening, but it's great. As always, people should read the Mythical Man Month. There's a lot of like.
It's anachronistic. No, it's not anachronistic. It's old.
There's a lot of programmer bro books that are always recommended. Mythical Man Month is always in there, and I read that kind of expecting it to be in that, but it's anachronistic, it's old, and it actually has like a ton of good advice that nobody follows. You know what I mean?
I for some reason when I read it thought there was like a pentagram diagram in it describing the like how many links of communication there are between like n number of people on a team. And I was looking at it earlier this week, and it's actually like a line chart. For some reason I just hallucinated that it was like a graph. But yeah, I pull that out all the time when someone's like, we need to add someone else to the project. I'm like, count how many lines can you draw between all those people? And they're like 25. I'm like, we don't need to add anyone to the project. Why would you say that?
Indeed. I want to learn more about Aiken.
Me too.
You would say that you have avoided.
I really need to do a Harvard Mark I episode.
Mark I.
I don't. That's one of those things that I think I built up to be a lot more background research than I think it actually will be.
I mean, it really seems like. I think it's more for me. The thing I'm interested in Harvard Mark I is not the Mark I itself, though that's interesting in that it's kind of one of those odd Zeus kind of area, like a computer, but not a computer like you would think of it. But it is a computer
program, which those are all weird.
But I mean, and it's mechanical to a certain degree, and it's
no
very
actual
funky.
mechanical.
Yeah. But Aiken is one that, like, I feel like there's a lot of computer science history people that, like, you know a lot about them, and like they show up a lot. You know, you always hear about the ENIAC boys.
Oh, John and John. And John, who also helped John on it.
Yeah.
And John.
I was going to say, and von Neumann shows up a bunch. There's another John. And so there's always, like, there's these kind of recurring characters, you know, and there are a lot of, like, background people. Like, I want to learn more about the EDSAC. Apparently the guy who designed the EDSAC is actually a very interesting person and wrote a book that I want to read that we should probably both check that one out. Because I didn't know. Like, and my library system has it. But anyway, to get out of this total...
I hadn't realized that he started one of the first comp sci degree programs.
Iverson?
No, Aiken.
Oh, really?
Yeah. That was like I explained in the episode, that was the class that Iverson was teaching, was part of the new comp sci degree program that Aiken started in 1954.
I didn't pick up on that. I was so focused on Kenneth Iverson was developing this infrastructure kind of to
teach a class. But he was doing the class because Aiken's class. Like, we're doing a degree program. You can get a master, or you can get I think it was a master's initially in, not called computer science, but computer science.
I mean, because effectively, it's like you described in the episode. It's like, it's stats with computers and other things.
And business, doing computer business.
Yeah.
In 1954. What does that mean? Figure it out.
But that, and just Aiken being a figure who just kind of pops up and is like, I have an idea for a computer. And it seems to be not related to anything else.
Well, the thing is, there are machines that are related to the Mark I, very few of them. And I'm sure there's a lot more run-up to the Mark I showing up than we're thinking. Because that, with ENIAC, there was a lot of work that both Eckert and Mauchly did separately that kind of led up to them coming together and going, oh, we could get a grant, or we could get a contract to build a computing machine using this prior work we've done.
One thing that pops off the top of my head that's back to APL is, what are the relations between APL and BASIC here? Because you mentioned it a little bit, and it is because BASIC is more interesting, I think, than people give it credit. But
it's the workspace thing. So APL initially, when it starts running, is in a time. Well, initially it's off punch cards, but it quickly turns into a time-shared environment that's interpretive. So it's using an interpreter. And APL implementations even today tend to use interpreters instead of compilers. But it's still an interactive workspace. So you log into a time-sharing system, you have a prompt, you type out an APL program, you can examine it and edit it, you can run it and save it. Exactly the same as Dartmouth Basic, but APL is using an interpreter, Dartmouth Basic is using a compiler. Which...
was original Dartmouth...
Yeah.
Dartmouth Basic was originally compiled. That's one of the things that I know you... I mean, you specifically mentioned about that in the episode, and even still at this moment, I was like,
well, it sounds weird, and the reason that Dartmouth Basic is compiled is for quick feedback. It's so if a line fails to compile, it can instantly say, you have an error on line 5. And that ended up being... or it was decided that was quicker than doing that interpretively.
I do find... I mainly find that interesting that Dartmouth was compiled, was what I didn't realize, because BASIC is funny like that in that a lot of... you get the 8-bit era BASICs, and they are...
all interpretive.
Effectively interpreted. And then you get a little bit later, they start introducing, especially like in the 80s, 90s,
like QBasic.
People start introducing compiled BASICs, so you can take your business software that you wrote in 8-bit BASIC.
Funnily enough,
make it into a program.
Kurtz and Kimony that developed BASIC, they, in I think the 90s, write this book called Back to Basic, which I love. If you can find a copy, read it. It's weird. They have some very strong stances. One of them is they hate interpreted BASIC. They call it street BASIC.
Yo.
And they're like, it's just not right. This isn't what it's meant to be.
They're like the French Language Institute of basics. You've got the vulgar street basic out there, and we are the academic pure basic.
If it's interpreted, it ain't basic, according to Dartmouth professors.
I mean, there's nothing about basic that intrinsically makes it hard to compile.
No, and like that's the interesting thing with APL being interpretive is the crew at IBM just didn't really care about performance, and they figured if it's a problem, we can deal with it later, but they never had to. So why?
Yeah, and it seems it's wild that to this day it still just ends up like, not really. It still doesn't really matter.
I think part of that is I was getting into the weeds reading some of the period papers. Part of it comes down to because it's operating on arrays and like in-sized data sets, you don't get the same kind of performance hit that you normally do from an interpreter, right? Mm-hmm. Because you're saying, do this operation to all of these things. So it can just go chunk, 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 chunk.
That's what I was wondering, is that I bet under the hood, it's taking all of those and it's dispatching a bunch of parallel operations.
Yes. Or it doesn't even have to be parallel. It's just that it can do it in a repetitive mode instead of being like, interpret it, do this line. Okay, now do this line again. Okay, now do this line again. So I think it must be, if it's like an inner-outer loop, the inner loop can just run
I would bet
faster.
I would bet it's not even loop-based stuff, because this brings me back to a thought that I had when I was listening to the episode. Mm-hmm. So speaking of that moment when you were talking about computers being effectively linear algebra machines, and my initial like, I don't know, and then coming back to it, and coming back to actually agree with it, and a place where I will even more agree with it is that modern CPUs, and also modern means like even as of
1980.
I mean, yeah, but like Pentium MMX, the whole point of MMX is to do vector operations. Mm-hmm. And so modern CPUs, a lot of the real performance in them is doing vectorized stuff.
Mm-hmm. Graphics is linear algebra.
Graphics is linear algebra. But so that I would strongly imagine that in most APL interpreters, they're taking a bunch of that stuff and they are executing it as vector operation, like they are translating it to vector operations, running it through the CPU's vector processor, and that's a really
interesting thought, because initially APL is so far removed from how a computer functions, right?
Right, because it's a math language, it's an algebra, and it's a
it's non-imperative.
Yeah, well, I was going to say, when you said it's and when you were just talking about like it's a new math notation, I feel like there's a certain part in there that it's a new math notation where in that period of computation becoming a field, or automatic computation becoming a field, there's a lot of people looking for how do we concisely notate all I can think of is algebra. Please help me.
Are you thinking about algorithms? Yeah. So like, algo,
to be able to notate
mm-hmm.
algorithms as a mathematical thing, because algorithms haven't been so much a thing, and they become important when you're automating your computation. So the notation really isn't there. So there's this gut thing that I see APL as being in some lineage there, because it's like a way to take math and express algorithms more properly mathematically.
Well, that's exactly what it was
language for it
used for initially, right? With teaching and with the contract work that Everson does with McKinsey, is using it for communicating algorithms. So, funnily enough, you said, oh, it's not natural language about like communication, but it is about communication, just from the other side of things.
Yeah. I'm just, it gives me all the other side of things is a great way to put it, because like talking about that scale, where you've got people who are kind of trying, you've always got the pragmatic and the academic, almost are like two representatives of those sides. And listening to this episode, things that just float through my mind are that thing that I'd like to do more research and be more well versed on this, but the kind of recency of formal logic syntax, or like, because I again, I'm really a pleb, but that like formal logic and systems of logic is really a very like turn of the century sort of thing where it finally like becomes
like
I don't know a ton about
fully.
it, but like like there's ancient Grecian logic, and it's all very much a branch of philosophy until kind of like the scientific revolution in the 19th century, where people are like, wait, like we could, like, is this math? Picture of guy holding butterfly.
Hey, bro,
guy with giant mutton chops holding a butterfly going, the butterfly says logic, and he says, is this math?
I'm sure there are good resources on the history of formalized logic and the history of formalized mathematics.
But that's why I'd like to know more, because looking at APL, it's a lot closer to that history in the timeline than one would think. And that's, again, like that merging of logic and realizing that logic and math are, that logic is a subset of and can be described by math.
And to an extent,
kind of like the grand unification. And then that all of a sudden gets merged into computer science stuff.
So to an extent, going back to what you were talking about, having like the revelatory moment when something clicks together.
Yes.
That's what people have in the 20s and 30s with binary and mathematics, where they're able to say, oh yeah, theoretically, there are things that show that you can use binary transforms to decimal transforms, so you can do decimal math and binary. Well, we have these things that are kind of like physical binary systems. Oh my God, it clicks together and we get math circuits and we get computers. So it is like a grand unified connector occurring.
Guy in a waistcoat again. The butterfly is in his hand. It is a 1 and a 0, and he says, "Is this numbers?
Is this enough?"
It really is. It's great. Like all this stuff that's just like kind of not well respected theoretical stuff that people have talked about, that all of a sudden they're just like, wait, holy crap, this is relevant.
It goes together. It works. And that's the kind of thing that's really hard to do like the full historical treatment on, right? Because then you get into the problem of, where do I start computer history? Do I start at the first time a caveman counted rocks? Like, is that a computational method? And do I have to go find those rocks to talk about like the 1980s and home computing?
I think so. I do think so. Yeah.
We're going to do it. Field trip. Find the rocks.
Find the rocks. We're going to start a GoFundMe to help us find the rocks.
No, what I'm going to do is break into CHM next time I'm in the Bay Area, and I'm going to set up an exhibit in the lobby. So it's before the abacus. It's just 3 rocks, and I'm going to say primitive computational aid.
Perfect.
Yeah.
I mean, prove me wrong. I think hopefully we just keep turning up like things that are on my mind, or that like, oh, I remember this occurring to me as we talked about things. And thankfully we've gotten more and more APL relevant as we've gotten to the tail of this episode.
The rocks are very relevant to APL.
Yeah. I mean, the thing about talking about a language this early is that it just kind of ends up being relevant to everything.
Exactly.
And that's what makes it fun too. I will say fun stuff about functional. This is a place where I can do my last little bits about talking about functional versus and APL. And so firstly, there's a great thing that functional people will know, that I've always known this about APL for some reason. I think just because it comes up in searching functional stuff. So monads, especially because of Haskell kind of made them a thing. Monads are a thing in Haskell. They're a big thing in Haskell.
Okay.
And they are not monads in APL.
So they're different.
Because Iverson just chose the word monad because it is a cool word and it has mono in it.
So then what are they in Haskell? Teach me, because I don't read about Haskell.
It's a whole thing. It's a class of types of data that have associated operations. And there's a formal definition to it. In APL, of course, a monad just means it's a unary operator.
Yeah.
Yeah. And also there is some history there. Again, this is just because I've looked it up, because I'm like, what the heck? When you try and figure out what a monad is in Haskell, you end up accidentally finding out what a monad is in APL because that's not what you're trying to find. So it's the only thing that shows up. And then you're reading about the history of this on the wiki pages and you're like, this does not seem right. And I don't think I'm learning the right thing here, but unfortunately you are learning about it regardless. Monads are a whole thing. Like the idea of atoms in early, like I want to say 17th century history, especially. Oh no, it's talking
about Greek.
No, not that early. Isaac Newton's
Principia, the magic one.
No, sorry, I'm trying to think of names again. Isaac Newton's calculus adversary, Leibniz.
Yeah.
Leibniz had a whole
treatise on monads.
He was trying to merge together his religious convictions and his scientific ideas. So he had this idea of things.
You have to summon the demon first to make a computer.
It all comes back to the magic circle. But anyway, so that's where monads comes from originally, as I understand it.
Interesting.
Leibniz coined this term monad for...
That's really weird.
Basically like the minimal element that things can be made of, and that it was also what souls were made of.
So Joe, you're saying that makes more sense in Haskell than calling a unary operator a monad in APL? Because that doesn't make any sense.
I feel like unary operator, I just have a gut feeling. That feels like something that is less our modern parlance and more, he just chose this word because it was cool.
It's a cool word.
Leibniz had used it. And I'm pretty sure that's where it comes from. And yes, that dyads, for anybody interesting, there are dyads in APL, and they are binary operators.
Yeah,
so classic. Like addition would be dyadic.
Well, addition's also monadic because all functions are dyadic and monadic for economy.
Oh gosh, see, we keep
economic purposes.
Indeed.
88 characters in this economy.
It's currying. There's a thing in.
No, I don't want to learn about currying again.
I know, but it is because as soon as you apply an operator to one side of a binary thing, as soon as you've applied an operand to your dyadic operator, it becomes a monadic operator, right?
I don't want to learn about currying again and again.
No, I won't go there. That was strictly APL. I don't know any APL, but I have to assume that's how it would work. Is the
probably
when you monadically add terms on, it's because you are adding right hand sides to the binary operator. That you start with the left hand side and then you add.
Well, APL's right hand precedence, but I do get where you're coming from.
Yeah. Which I didn't quite realize that, again, until I was doing a little bit of trying to learn about this. You say in the episode, it's like, you read it right to left, and I'm like, man, just because it has the arrow doesn't mean it's right to left. And then I actually read, it's because the precedence is right to left.
Yes.
That's insane.
Yes. Well,
that is messed up.
So the whole point of it is so that you don't have special precedence rules. You have one rule, it's that you operate right to left. So you don't have
that's the wrong rule. That's the thing. Hey, you have one rule and it's wrong.
At least it is a system, dude. Right? At least it's not like I have my algorithm that has PIMDOS enshrined in it because everything has to have that enshrined in it. You can do PIMDOS, you just have to put brackets around it, and then you're fine.
I don't stand by. This is the problem. Don't learn too many programming languages, people, because then you just put parentheses around everything because you're not sure what languages have PEMDAS.
You just escape random things.
Also, I pray to God that was a Lebowski reference.
Oh, yes. No, of course.
Excellent. Okay. Say what you want about the tenets of National Socialism, dude.
At least they have right to left precedence for operating on mathematic functions.
No, say what you want about the tenets of National Socialism. At least they have left to right precedence. So there was a thing that I wanted to get to really when I started talking about monadics, all this monadic stuff. And it's that you talking about there's a little bit of blurb at the beginning of the episode that got me going about APL being functional, and the thing about functional programming being that like it doesn't have branches. And that's I also understand a bunch of APL stuff is like you can do a lot.
You can do branches
with non-branching code. APL that you can do branching, but that you can do a ton in APL, and that people do a lot in APL with non-branching code. Which also just people for as a side note. That's a whole interesting thing to look into.
People are an interesting thing to look into, Joe. That's correct.
Many of them, as it turns out. Some of them not so much, but a lot of them. To look into, stuff. I lost it. So let's just dive in. What I was going to talk about is non-branching code. I was going to say for people, there's a whole school of writing code that is, and writing even assembly that is non-branching because it's very performant and it doesn't cause cache, not cache misses, but jump misses. Anyway, that doesn't really have anything to do with APL. Functional stuff is talking about functional programs not really having branching, which is not really correct.
Okay.
And it's not that I want to correct you.
No, I'm not an FP guy. Correct me, please.
And you were right. Like, it was good to talk about like in pure functional languages,
Yes.
which is Haskell is basically the only one that exists. There's also a language called something. There's a language that it was inspired by, Miranda. There's a language called Miranda that it was inspired by, but like those are the only pure functional languages that realistically exist. But you can think of it as like a step function, because everything's an expression, but you can branch by having effectively a step function where you're saying, if this, then evaluate to this. Otherwise,
Gotcha.
it's a ternary.
But a ternary is just like you're hiding a branch.
Right, and that is all it is. But that leads me down the path of, it makes me think about lambda calculus versus Turing machines. And again, that interesting early history of figuring out what is this computing thing. And that, as I've gone over, and it's interesting, the Turing Church thesis, the last time that I brought it up was just that it is very interesting in that it only expresses itself. The whole thing about the Turing Church thesis is that it proves that one is equivalent to the other, and then
which is important.
Calculable is calculable, and it just exists in that little bubble of its own thing.
But the bubble's very
this
big.
time, it's the other way around, because it actually is relevant in that Church Turing thesis proves that lambda calculus and Turing machines are equivalent, and that's the thing about functional languages is that
the same as
you can write a mathematical, you can write a assemblage of functions that evaluates the same thing that a imperative Turing machine does. That's an interesting thing about looking at like this APL world. That's really what it is that's what it comes down to, is it's the bridge between functional and imperative stuff. And that's, APL is kind of cool to me in that it's sitting there right in the middle, and that you're getting into this talking about APL being able to express, all computable things. It's a totally fully featured Turing complete language. And yet it does it using a bunch of these functional compositional ways of, which we've talked a lot about composition up at the front. And if people don't know, what we're talking about is making a function, an argument into another function.
And smashing functions, making a larger together.
Yeah, it's your high school f of g. Take your f, put g in as the argument to f.
That g is the next function name after f.
It really, talking about like early math notation.
Why do you got to do that?
All of this stuff, so arbitrary and only recently formalized, it really is so recently formalized.
So this is the history of mathematics, the podcast now.
It is. And it's because APL is rich and touches all of these things.
It really is. And going back to why I keep being drawn to being stuck in the 1940s, foundational periods to me are really, really interesting because they touch so many things. And I'll always go back to, if you understand the foundations, you'll go completely insane seeing echoes of them everywhere. And that's neat.
Yeah. Yep. And seeing the things that you take for granted as making sense, especially in terms of like syntax or symbols used in a way that we talk about something. And it is that somebody made those arbitrary choices in one of those like big bang moments of everybody scrambling on something, or something like being a hot new thing, and then it just becomes the stuff we use, and we take it for granted.
Standard.
Yep. And that's, Newton and Leibniz. You go back to their notations. There's that's the one that I think a lot of people, if you've done math, are at least a little bit aware of is, your dy over dx versus your, nobody really knows that, because Newton.
I always get them mixed up. I get them flipped backwards.
So at least this is one that I actually do know. Newton, Leibniz is dy dx.
Which is better.
Which is better. It really is.
You can cancel out dx. You can just do it. If you have two dx's, you can cancel them out.
It is a ratio of infinitesimals, and as much as mathematicians will tell you that you're not allowed to say that it's a ratio of infinitesimals, it is a ratio of infinitesimals, and it does work.
I'm a dumb knuckle dragging physicist. I was just taught dx that you can cancel that out and you're fine. Don't do it in front of your math professor; they will hit you.
Yeah,
and all of that is true,
undoubtedly. But yeah, and Isaac Newton has his is the tick marks, and I don't know because tick marks are for I think
they're like the hat, or they're not. I don't know what his, but they're dot.
Or wait, no, because and he I think has the elongated S integral notation because Leibniz uses some. Again, I don't because I never got into differential equations and stuff where you're using a lot more of that notation in school. But anyway, my point there being is that people are relatively familiar with those existing, and it's important to point out, especially with something when you look at something as odd as APL and its weird character syntax and its way of doing things, is to understand that a lot of these things are so arbitrary, and especially talking about math in particular, prior to the modern era, everybody's just kind of writing it down their own way. And that's why you even get those. And so you end up with APL, and they're just trying to take all of these. I mean, things are still coalescing. And that's why, coming up with our own character set and using weird notation is just trying to continue this formalization process.
So listeners, if you have a recommendation for a good book on the history of mathematical notation, please write into the show. I'm also all here for it. I'll read it. I'll read a book. I'm
down. If not, I will end up becoming the researcher that whenever I retire, I will dedicate my life to writing my old man book of the brief, understandable history of mathematical notation.
I think that would be really interesting. Anyway.
It all comes back down to mathematical notation because that's at the beginning, the alpha and omega. What APL is about is
a programming language.
It's a programming language, and it's going to be terse, and it's gonna do a great job.
It's crucial to the economy that APL is terse. I don't know why, but it is.
It is.
It is.
You can't argue with it. I think we've bled this one dry. Thanks for following us on. I feel like every episode we're even more and more tangent heavy, and that is just wonderful. So thank you for following us along on all the twists and turns, everyone. Thank you, Sean, as always, for hanging out with me for an hour and shooting the shit about whatever it is that we are here to talk about. And until next time, thank you guys for joining us on Adjunct of Computing.
Catch you around.
See you around.